Okay, so you've already seen that the mean of a binomial distribution can be found quite simply and easily just using this formula NP, which is quite intuitive. It's simple to use. Now the proof of it is actually quite complicated, and the proof is not something that you need to be able to reproduce in an exam setting. So effectively, you probably don't even need to copy this down. But as always, I don't think it's wise to use a formula unless you've seen where it comes from and you have some notion that it actually does work. So I think for this video, you could just follow along, see if it makes sense, and then you can carry on just using and applying that nice simple formula. Now, if we have a binomial distribution, we denote it this way with the letter B, and we say it has n number of trials, probability of success P. What we're talking about then is some sort of binomial expansion where we've got P as the probability of success. Q is, of course, 1 minus P, or the complement of P. Raised to the power of n, that's our number of trials. Now, if we define x as the number of successes and p as the probability of success, then I think you can imagine here that this is a big, long expansion, and we could just say that any one term in this expansion is n choose something, let's say r, p to the power of r, q to the power of n minus r. And we've seen also that we can mix those two indices around because we've got that. If we mix them around, we can replace this r with n minus r. But this is the more standard way, I suppose, of looking at it because the number of successes can be put in here as r, and we've got n choose r. So I think this is the simpler version for this application. Now, expected value, mu, two equal things that we can call it. We've already seen how to calculate this in year 11. It's the sum of all of the things that could happen multiplied by the probability of each one of those things happening. So our standard way of working this out in year 11 was to make a simple table and say, well, let's call x all of the things that could happen. We might get 0 successes, 1 success, 2 successes, 3 successes, 4, etc. And then we look at the probability of each of those things happening. And then we say, all right, let's multiply each thing that could happen by its probability. And we ended up with a table, simple table that looked something like this. And we said, all right, if we take the sum of any row, then all of the probabilities have to add up to 1. But the sum of all of these things is actually mu, or the expected value. So let's think now how we can fill these boxes in to come up with this formula. All right, we've said that any one term can be found using this. So if we say, well, what is the chance that we get no successes at all? That's allowing p to be raised to the power of 0. And anything to the power of 0 is 1. And n choose 0 is also 1. So this term and this term would both be 1, and we'd just have q to the power of n minus 0. So we just have q to the power of n. All right, what about if we're looking at letting r equal 1? Well, we're going to have n choose 1. P to the power of 1, obviously that's just p, but let's generate a pattern, and q to the power of n minus 1. If we let r equal 2, we've got n choose 2, and we can see a pattern here that we're going to have a choose number at the start of each term, and then we can have p 2 successes, p to the power of 2, and q to the power of n minus 2. And similarly here, we'll have p cubed and q to the power of n minus 3. And this pattern can continue on. So then if we multiply each of these terms by their probabilities, 0 times anything is 0. But each of these terms will effectively need to be rewritten just with that number out the front. So we've got one lot of n choose 1, p to the 1, q to the n minus 1. And I'm leaving those ones in there just for completeness here. 2 multiplied by n choose 2, p squared, q to the n minus 2. 3 multiplied by n choose 3, p cubed, q to the n minus 3, etc. So clearly, our mu is the sum of all these terms. Now, to turn these into a different format so that we can quickly and easily come up with this, we need to use a little trick. Now, the first trick that we can use is that we can notice that each of these terms is going to have something in common. It's going to have at least one p in it. Now, I can see that bringing a p out the front is going to be helpful because this is sort of my finish line, I guess, and it's got n multiplied by p. So first step is I'm going to bring p out the front. Let's say mu is now equal to the sum of all of this So it's going to be p multiplied by, and let's use square brackets here, to say now we've got 1 times n choose 1, which is just n, but let's write it, n choose 1, multiplied by q to the n minus 1, plus we've got 2, n choose 2, p to the power of 1, not 2 because we've brought one of those p's out the front, q to the n minus 2, etc., etc. So I can start adding these terms, and each time the number of p's I've got is just one smaller, plus, etc. Oops, let's use square brackets on the end. Now, to continue to simplify this, we actually need to do a bit of working on the side and come up with an identity that helps us change the format of each of these terms into something else. Now, this is not something that's intuitive, that you look at these and go, oh, I know, I'll use this little trick. When you look at it for the first time, you can see how it works, but at the same time you think, well, I might not have come up with that on my own, and that's completely fine. Now, have a look at what we've got here. We've actually got 1 times n choose 1. We've got 2 times n choose 2, 3 times n choose 3. So if we say, all right, let's have a look at that. If we've got some number, let's call it x, and we're multiplying it by n choose x, what does that actually look like? Well, it looks like x multiplied by n factorial over n minus x factorial, x factorial. So there I'm just using the basic expansion of this, and we're getting there. All right, what can we do with it next? Well, we could actually expand this whole line so that we've just got a giant fraction, sure. We could also take n factorial and we could unroll it. Let me move it on to make it a bit easier to see. We could unroll the top, so we've got x multiplied by n multiplied by n minus 1 factorial on the top. And down here we could unroll the x factorial. Now, why would we want to do that? Well, because then we're going to have an x out the front, and that's going to talk to the other x. So let's leave the n minus x factorial rolled up, but let's unroll this x factorial into x minus 1 factorial. Okay, now our x's cancel, and we've got this. Now, let's pull the n out the front and just leave it all by itself. Why am I going to do that? Well, I can see that in the end I kind of want the n on its own, so let's get rid of it now. And we can see that now we've got n minus 1 factorial over n minus x factorial, x minus 1 factorial. Now, that might not look super familiar to you, but what that actually is n multiplied by n minus 1 choose x minus 1. So we get this. So we've changed one fairly simple looking term into another reasonably simple looking term that has a completely different number out the front. Now, just to verify that this actually is the same as that whole part there, let's use another colour and just check our work. And let's say, well, hold on a minute. What is n minus 1? Choose x minus 1. It's n minus 1 factorial. And then on the denominator, you need to say, I've got n minus 1 minus bracket x minus 1. All of that in a factorial, multiplied by x minus 1 factorial. So you can see here that the x minus 1 factorial is on the bottom, that's fine. The n minus 1 factorial is on the top. And if we tidy this up, we've got n minus 1 minus x plus 1, and the 1's are going to cancel. So that whole part there gives us the n minus x factorial, which is what we had here. So I think with that bit of working, we can see now that that is actually equal to this. All right, back to our main working then. We can take each of these terms, the 1 times n choose 1, the 2 times n choose 2, and we can use this formula to change it. So we can see then that if I let x be 1, then 1 n choose 1 becomes n. Now, what's 1 smaller than n? It's still n minus 1, but x minus 1, if I'm letting x be 1, is just going to be 0. So down here now, I'm actually going to have still my p out the front, and then I'm going to change this term into n minus 1, choose nothing. Okay, so can you see how 1 n choose 1 can change into n minus 1 choose 0? It's still multiplied by q to the power of n minus 1, and that's my first term changed now. For my second term, 2, n choose 2, well, if I let the x be 2, n is still n, then I'm going to have n multiplied by n minus 1, and I'm going to get n minus 1 on the top. all the way along in every single term, but x minus 1, if x was 2, is just a 1 on the bottom now, and that will be multiplied by p q to the power of n minus 2. For the next term, if x is 3, then I've got n minus 1, choose a number 1 smaller than 3. And you can see that I'm building up a different pattern here now. Okay, what can we do next? Well, next it makes sense to look at our finish line and say we're looking for NP. We've got P out the front, but clearly now all of our terms have N in them. So it makes sense on the next line, a little bit tedious to write it out, but let's bring N out the front of our brackets. And now we've got all of these terms. I can notionally write in here, this is P to the power of 0, just to continue a pattern. And I've got N minus 1 choose 1, P to the power of 1, Q to the power of N minus 2, plus, etc. And I can write as many of these as I like, probably 3 makes sense, just so that I can actually show a pattern there, plus. Okay, now, having a look at what we've got inside of the square brackets now, this looks sort of familiar. It looks like a binomial expansion in its own right. But what are the parameters? Well, we can see that here we've got n minus 1 choose 0, n minus 1 choose 1, n minus 1 choose 2. Normally, in a binomial expansion, we can see that that number at the top of the choose notation is actually the number that is the power in the binomial expansion. So here, it looks like we've got something plus something to the power of n minus 1. Now, it looks good, except I can almost hear you thinking, but don't we need to have, if this is p to the power of 0, n minus 0? No, because we've actually got n minus 1 here. So let's just put in some parameters here and say, is it p plus q to the power of n minus 1? And we can think about whether it is or not. Well, any term in this expansion is going to be n minus 1, choose something, and then we're going to have p to the power of r, and then we're going to have q to the power of n minus 1 minus r, aren't we? Because n minus 1 is our power. And is that what we've got in each term? If r is 0, then sure enough we've got p to the power of 0, and then we've got q to the power of n minus 1 minus 0. That is exactly what we've got here. What about if r is 1? We've got n minus 1 choose 1, p to the power of 1, q to the power of n minus 1 minus 1, which sure enough is n minus 2. So yes, this is this expansion. Now, let's come back to what p and q are. P plus q equals 1 because they're probabilities and complements, so they add up to 1. So that means 1 to the power of anything, no matter what n is going to be 1. So this whole thing now equals 1. So therefore, the mean is just equal to np, because we've multiplied it by 1, and all of this cancel it out to be 1. And that's the proof of our formula here, which we've already learned how to use